All right, now we will start a new subject, approximating areas. So the topic that I want to cover is, let's say you have some function y equals to f of x, whose graph is given, and my goal is to find the area under the curve inside, under the curve over the interval given. Okay. That's the fundamental question I want to ask. Now, we've been doing antiderivatives so far, and it seems like a complete different subject that we're dealing with now. But you will see later that they're very much related. In fact, the way you find the area over this interval is you have to find the antiderivative, and the difference of the value of that antiderivative at these 2 points would indeed give you the area. That's what you're going to see later. Now, but before we get to that point, we will first talk about various approximation methods for finding area. So let's say you have y equals to x squared. Let's think about a very simple example. And I'm interested in the area under the curve over 0 to 1. The question is, what is this area? Well, actually, you do use a lot of these approximation methods in engineering. So I heard that one of the naval arc class has this question like, oh, you have a hole in a ship, and then you measure various parts. You find so if you have a hole, let's say you found these lengths, okay, and you know how far they are apart. Okay. Can you find the area of this irregular spot? So let's say it's somewhat like this. Okay. What's the area of this hole? So you can figure out how much water is going to come in under what pressure, right? And for these types, there is no equation for the shape of this thing, right? So you can only measure things, and you can record it, and you have a bunch of numbers, okay? And in that case, you can only talk about approximation. You can't talk about the actual value of the area. So what I'm trying to do is, at this point, although we know the equation for it, we'll for a moment just forget that there was an equation for it, and let's talk about like trying to measure various height of this function, and from there we'll try to get an approximation of the area. That's our goal. And by the way, what we are learning here will be actually be used in that engineering course. Okay? Students have been coming to me and asking me like, well, what's the Simpsons rule? Can you explain it to me again? Okay? Because they forgot. All right. Yeah, we're going to learn something called Simpsons rule, which is the best approximation method in such cases. Right? All right. So here's one approach. So let's draw it big. Now, one approach would be to divide this into 10 equal parts, like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5. Okay, sorry for the crappy drawing, but I'm supposed to, I meant that this is like, this one is 0.1, 0.2, 0.3, and so on until 1. All right? Now, one way to calculate the area is to do, use rectangles. And there are actually several ways to use rectangles, but here's one method. One method is to use a rectangle whose top right is touching the curve. Now, such a method is called right sum. So, approximation. Right sum approximation, and basically what you're trying to do is build rectangles so that top right corner touches the curve, the graph. Okay? And of course, immediately you would know what it means to be a left sum, right? Yeah, left sum would be the case where the top left corner will be touching the graph. Okay. Now, let's calculate the area of these things, and I'm going to name them R1, R2, and all the way to R10. Okay. If we have the area R1, R2, R3, R4 until R10, and we add them up, what are we going to get? We'll get something that's close to the area of the real thing, right? Now, would that result be an overestimate or underestimate?
Over.
It would be an overestimate because there's several things sticking outside the area, right? So we see that the right sum in the case where the graph is increasing will be an overestimate. You could write that down, but it's so obvious. You just have to draw it, and it's just so obvious. You probably don't have to write that down. Okay. All right. So let's do an actual calculation. All right, so for all these, the base length is what? What's the base length?
0.1.
0.1, right? So we always calculate the area of a rectangle by taking base times height. So R1 would be 0.1, that's the base. And what's the height of this rectangle? All right, so this location is 0.1. How do you get the y value when you know the x value?
Plug it in.
Plug it into the original function, right? So if you plug into original function 0.1 squared, you're going to get 0.01, right? Let's just write 0.1 squared for now. That's some value. And actually, it's better to just leave it like this and then add them up later. Okay. R2 would be 0.1 times 0.2 squared. R3 would be 0.1 times 0.3 squared, and so on and so on. Yes?
Why couldn't we just do like 5 rectangles and then split it up that way instead of...
Oh, yeah. So that's a good point. I split this up in 10 rectangles, and it seems like a lot to calculate. The question is, why can't we just use 5? And actually, that's just something that you decide, or the question would decide for you. So often the question would be something like, use n equals to 5, and in our case, n is equal, this case would be n equals to 10. right? So use 10 rectangles and write sum to approximate the area of the given thing. That's how it's given. Right? Yeah, for me, it's easy enough, so I just did this. Any other questions? Oh, another thing is, if you want better approximation, do you want to increase n or decrease n? Increase n. You can see that if you use like 100,000, then you'll get better and better approximation, right? Okay, so what you end up getting is, if you have R1 plus R2 and all the way until R10, this is what you're going to get. See, every one of them has 0.1 multiplied. And then this is 0.1 squared, 0.2 squared, way up till 1.0 squared. And then you can add this up. Okay. All right. Now it happens that I know some math that you don't know. So of course you should be using a calculator during the exam if you were given something like this. But I can actually do this in my head. Actually, I'll have to write a little bit. It'll be this is what I'll do. Everything has it's 0.1 times 1, 0.1 times 2, 0.1 times 10. So I can pull out a 0.1 outside. Okay, and then it'll be like 1 squared plus 2 squared plus 10 squared. And this is like 0.001. Right? 0.1 times 0.1 squared is 0.001. And this one happens to have it has a really nice pattern, right? So it has a nice formula, which is like that last number times the last number plus 1, and then you do twice of the last number plus 1, which is 21 over 6. So if you do this, you get this answer. What's that? That's let's see. This will be 7, and that will be 5, 35, 35, 385. That will be what you get, and therefore you get 0.385 as your answer. Okay. So that last part I'm not requiring you to know, but it's something nice to know if you are good with math. So what I'm trying to say is that if you have 1 squared, 2 squared up to n squared, this answer becomes like n times n plus 1, 2n plus 1 over 6. Okay. So that's a nice formula. But you don't have to worry about that part. All I'm saying is that suppose you had a calculator and you had enough time and you plugged everything in, you would get 0.385. Okay. So what does this mean? That the actual area is more than or less than what?
Less than.
Less than 0.3. That's what it means. All right. Now let's try to, I'll just erase this if you're not interested. I'll erase this one too. Let's try to come up with a general formula for a right sum. Okay. So what is the right sum in general? So suppose you have a function f of x, and you have the interval a to b. What does it mean to find the right sum? Okay. So here's the procedure for the right sum. So first, you calculate something called delta x, and delta x is really the base length. Okay. How would you get the base length? Well, you have the total length. What's this length?
B minus A.
B minus A. If you subtract the 2, you're going to get this length. And if you have n rectangles, how do you get the base length of one rectangle?
Divided by N.
Divide by n. That's delta x. And actually, we're going to learn many other methods. So there will be like right sum, left sum, trapezoidal, Simpson's, midpoint. There are many different methods that I'm going to introduce. This is the simplest of all. And regardless of the method, this will always have the same meaning. Delta x would be the base length, and it's b minus a over n. So that's the first thing that you would want to write and calculate for any kind of approximation methods. All right, then we have another naming convention, which is good to follow, and it's like this. We call the left endpoints as x0, right? And the next stop as x1, all the way till the last one as xn. So x0 until xn. And of course, x0 is a itself. What is x1? Well, this delta x is the step size, right? So it's like I start from this one side, which is A, and I start walking towards to the other side, which is B, right? And every time I walk to the next step, my step size is how much? Delta x. So I walk delta x, delta x, delta x, and then I eventually reach the right side. So x1 will be A, and you move one step to the right by delta x. x2 would be A plus 2 delta x. x3 would be A plus 3 delta x, all the way up till this xn, which is A plus what delta x? And these two should match, right? So if it's 3, that's 3, 2, 2, that's what you do. Okay? So that's the naming convention. And at each of these, you should also know the height. Right? Height at each point, right? So what is the height over x0? Well, the value, the y value is the height of these sticks that I build over each of these sides, x1, x2, x3, x, and all that. So you have to evaluate the function at that x location to get the height. So y0 is this, y1 is f of x0, actually x1, and so on and so on. And therefore, what we get is, it's like this. So if you go back here, look at what's happening here. This is delta x in that general picture, right? This is delta x. What did I do? I plugged in the x location into the function. So this is like y0, y1 actually. So the 0.1 itself is x1 because a is 0, x1 is 0.1, x2 is 0.2, x3 is 0.3. That's what's being done here. Okay. So if you're doing the right sum, this is what's happening. You ignore the x0 because that's not used. You start using x1 as the pivot for building the first rectangle. So you build your first R1 like this, right? Maybe I should just erase everything. Okay, so what's the area of R1? Base length times f of x1. R2, delta x times f of x2, which is, this is right like that. Okay? So then you add them up. So until Rn, you add them up, you get the approximate area, right? That's our plan. So if I write that down, here's the formula for the right sum. And if you found this part boring, I'm sorry. It's just this thing that you really have to know. So here's the formula: R sum equals to delta x times f of x1, but x1 is a, right? No, a plus delta x. A plus delta x plus f of a plus 2 delta x, because that's x2, this is x2, plus f of a plus 3 delta x, and all the way until you reach the last one, which is a plus n delta x.